Again, this is Dr. Ali Mughebel. Before we continue with multi-carrier and OFDM communication, we need to understand the capacity of a non-ideal linear filter channel. So if we have a channel that is band limited, what is the capacity of this channel? We will start with the ideal channel. So recall that the capacity of an ideal, which means the amplitude of the channel is constant, the phase is linear, and it is band limited. It has a bandwidth of W, and we assume the noise to be additive wide Gaussian noise channel. What is the capacity? We found out through channel capacity that the capacity of the channel C is the capacity measured in bits per second. W is the given bandwidth, is the channel bandwidth, and this is the average power, how much power we pump into the signal. So we expect the capacity to be proportional to the bandwidth and the average power. We also expect the power to be inversely proportional to the noise bandwidth, the noise power. So a note is the noise power spectral density, watts per hertz, multiplied by the bandwidth, give you the noise power. So to sum, this is the signal to noise ratio. So the channel capacity of an ideal band limited channel is proportional to the bandwidth, the average power, and inversely proportional to the noise power. So in a multi-carrier system, what is going to be different? So this is the channel, the ideal one. The non-ideal will have non-constant amplitude. And for the multi-carrier systems, we can divide this into smaller channels. We can think of channels of bandwidth sufficiently small to make every strip here, every communication bandwidth to be almost constant, so the variation within the bandwidth can be assumed to be ideal. In that case, we can assume that the capacity of this small channel, C sub I, because we have many of them, equal to the new bandwidth, which is delta F, and of course we have the noise power will be SNN. Okay, multiplied by the delta F. Now the bandwidth, the noise bandwidth is also smaller, and from here we have the power of the signal in purple or violet color. For N naught, it's equal to the power spectral density divided by delta F. So delta F, now I am taking it at the top. Okay, now we can see that delta F will cancel with delta F, and we can state that the capacity is basically the remaining terms. And if you want to consider the entire bandwidth, we need to sum up. So C, the total capacity of the multi-carrier system, would be the summation from I equal to 1 to capital N, where N is the number of subchannels, over that capacity. So we're going to add basic summation of all. And if we do that, we have the following expression. Remember that delta F cancels with delta F. So this is the total capacity for the multi-carrier system. We should see some advantage from going to here, or going from the non-ideal case to this case on the capacity. All right, so if you take this discrete equation and we take the limit as delta F goes to 0, as we make the channel very small, it becomes almost constant ideal. That's in the limit. So you can see that this summation is going to become like an integration, and we'll have the differential. So I'm going to move then to the next slide. Remember that this equation will be repeated, but with integration. So as I mentioned, as we take the limit as delta F goes to 0, we obtain the capacity for the overall channel, and the summation now become W. That's the overall capacity. We have a constraint. If you want to compare the multi-carrier with the single carrier, the constraint is that the power that we pump into all the carriers, all the channels, should be less than or equal to the average power in the case of single carrier. Otherwise, the comparison will not be fair. So the choice of the power that maximizes the capacity should respect this constraint. So this is the capacity that we want to maximize, and we're going to embed this constraint, and it's going to show as a Lagrange multiplier by BF. So to go from here to here, we kind of embed the constraint. We're not going into the details. I might share some videos. There are lots of videos that explains how the exact mathematical derivation. But for this video, we're just interested in the result. So lambda is a Lagrange multiplier, and we mentioned we added this to satisfy the constraint. Now, if you go through calculus of variations to perform the optimization to find where are we going to get this to be the maximum, you will find that the optimum distribution of the transmitted signal power is obtained from the solution to this equation. Again, this is using calculus of variations. Remember that our objective is that we want to know how do we distribute the power over all the carriers, over the individual carriers. So taking this as the solution of this equation to be the solution of this optimization problem, we'll find that lambda is a constant, and for that to be true, this denominator must be constant. So this has to be constant, and this constant will make it equal to k. So now we can say that for this to be constant and it's equal to k, then if you equate to k, then the amount of power which we search for should be equal to k minus this quantity. So the average power constraint is given by the following: power as function of frequency equal to k minus this term. If you focus on this term, we have the noise in the numerator. So this is kind of almost an inversion of the signal to noise ratio, the opposite of the signal to noise ratio. It's in fact it's the signal spectral density, the noise spectral density divided by the channel gain squared. So it's somehow related to the opposite of the signal to noise ratio, and of course it's going to be zero. The power will be zero, of course, outside the spectrum of interest. Now, on the left-hand side here, I'm showing you a practical example of a channel where we see that the frequency response is not constant of the channel. So that frequency response will be inserted here. So we can see as we increase the frequency, we have less signal and less. But this term is not the signal to noise ratio. It's kind of the inversion. So if you invert this equation, you'll get, whenever you have low, you will get high, and so on. So if you plot that as function of frequency, or for one example, we might get the following curve. What is this curve? It is SNNF divided by the channel squared. This is, like, as I mentioned, kind of inverse of the signal to noise ratio. Now, if you want this to be, if this is k, if this is a constant, the difference between this k and the curve is the power. So here we have the following quantity, at this frequency we have the following quantity, and so on. So if you think this of a water reservoir, what you are trying to do is to fill the water here. This is why we call this equation a water filling algorithm, where we or interpretation, where whenever the noise become low, you need to utilize this channel, and then you have more of the power being pumped there. If let's take the example where we have zero noise. If your noise is zero, then we'll have a constant. We'll send that power, which is constant. As the signal become more, or the channel become more noisy, we will have to utilize it less, and of course the required power, if the signal, if this term becomes more noisy, then we'll have to utilize it, or the noise become less, then the amount of power will be higher, which means we'll make use of this channel because it's a good channel and we need to utilize it. So you can think of this interpretation, take your time, pause the video and think twice. We have the signal to noise ratio, we have the inverse of the signal to noise ratio, and we want to find the power as the strips here between K and the curve of interest. That give you PF. So that's called the water filling, and this tells you how to distribute the power at different frequency or different carriers. Outside, it's going to be zero. So we'll continue with the OFDM as we have seen how to distribute the power, and I will going to share some videos for the detailed derivation of this analysis. You can find that in the comment section. Thank you, and see you in coming videos.